Happy to be here with you. Regretfully not in person, but I really hope this will be useful for you, and I'm happy I can be here with you on the screen. So today what we're going to do is look at how to tune our Kubernetes deployments for performance, but not just performance, but we'll dive further into this later. So the whole idea of this is being a workshop, a hands-on workshop. And in order for that, I'd like you to first of all enter the virtual labs. And you can see the link on the screen. So please type this into your browser address bar. It's t.ly rbx capital P small p. Now, when you type this in, you'll be taken to the stgo environment right here. These are virtual labs provided by a service called stgo. There is a very short sign-up process there. The easiest way to sign up is with your email. The easiest is with Gmail, of course, but you can also sign in with your work email. And once you're in there, you'll be requested to input the token, and you can also see it on the screen. So I can see that there are already 2 folks who joined, and we'll wait for a few more to join. And let me show the screen again. So this is the URL, and this is the token. Now, once you enter the link, you're able to communicate with me through the chat. You'll notice that the environment has a chat. So you can send messages here. Now, regretfully, I can see how many of you are there in the classroom. So I have no idea how many of you are supposed to join, but we'll give it a couple more minutes. So whoever is maybe late to the show and just entering now, there's a URL on the screen. If you want to participate in the workshop, to do the hands-on training, please type this URL into your browser's address bar. This will take you to the stgo virtual environments. You can type in the token there after you sign up with your email, and once you're in there, you can start participating in the training.
In the classroom, we actually have 3 people right now, I see. So I'm not sure if there will be more.
Okay. That's totally fine. Okay. So a little introduction, a few words about me. So this was originally announced as a Kubernetes performance tuning workshop, but I then realized that it's not totally correct because you cannot talk about performance without thinking about additional concerns, and we'll talk about this later. So I further renamed this to a Kubernetes optimization workshop. Optimization is a long word, so there is also a numeronym for it. So it's O10N. A few words about me. I'm Anton. I've been in the industry for more than 20 years, and I've went the whole path from being a software developer in C and C++, through doing all kind of integration stuff, the twilight area that nobody had a name for a couple of years. They called it integration, configuration management, release engineering, and then at a certain point I realized what I was doing all along the way was called DevOps, and that's what I've been doing for the last 10, 15 years. Went very much into cloud and cloud native about 10 years ago. Have been teaching Kubernetes for more than 6 years and doing Kubernetes deployments for organizations, small and large, doing consulting. Now, this last year, I've been working very actively with this startup called Perfect Scale that has an online service that allows you to keep your Kubernetes clusters optimized. Now, I've been dealing with software delivery optimization for all these years. So optimization is a topic that's very dear to my heart, and that's why we're here. Okay. So, first of all, as I said, performance. I'm not sure it's fair to talk only about performance because performance in software is a very elusive concept. There are lots of questions about how to define performance. Are we talking about throughput? Or maybe are we talking about latency? Or maybe we're talking about resource utilization, right? And when we're looking at that, do we care about mean or 99th percentile? Or maybe we're not concerned with any of these. We don't care about throughput or latency. What we care about is business metrics. I don't know, how many products are we getting sold, right? How much money are we earning? And we don't care what the latency or the throughput is. Maybe for what we're doing, this is not important. And when we further look into this, we realize that performance in information systems is inseparable from such concerns as cost, right? So usually when we want to get more performance out of the system, no matter how we define it, we need to pay more. If it's in resources, if it's in the architectural effort or development time, and reliability, of course. So if we want to squeeze out more performance for the same amount of money, then our system will probably be more performant but less reliable, right? And if we want to spend more money, then we can probably get both reliability and performance, but that's not a promise. Because many of the systems that we're looking at and we're trying to optimize, they are usually over-provisioned, which means we're paying for much more resources that we actually need, but they're still not reliable enough. Okay, so these concerns are all interconnected, and when we optimize, we need to look at them all. Now, it all boils down to basically resource allocation and utilization. Because in the end, you know, the way our system performs is very much dependent on that. Now, when we talk about Kubernetes, we usually talk about, you know, there is this difference between the control plane and the data plane. When you run your clusters in a managed environment, right? So if you're doing, you know, running Kubernetes on AWS or on Google or any other managed Kubernetes service, you don't have too much control of the control plane performance because the cloud provider takes care of that for you. But you do always have control over the data plane. We will be talking mostly about, actually only about optimizing the data plane, only optimizing the performance of the applications that we're deploying on Kubernetes. Control plane itself can also be optimized, definitely. You know, etcd, if you're using that, can be optimized. The Kubernetes internal components can be optimized, but we're not talking about that today. And that is important to you only if you're building and running your own clusters on your own hardware, which is not true for all of us. Okay, this was an intro. So for today, and by the way, if there are any more folks who joined, just so that, okay, in a moment I'll show you what we're talking about. So first of all, our training environment, right? So this is called stgo. You can see the slides here. You can see them on the screen and also in your own browser. When I switch slides, you see the slide that I'm looking at. If you want to leaf through the slides yourself, you can flip the switch here, unfollow the presenter, and then you can leaf through the slides yourself. All of these slides are also available online, and I'll give you the link in a moment. Not here. Okay, it's right here. Second. Okay. Now back to stgo. Okay, so these are the slides, the easiest way. Then the next tab here is called whiteboard. So if you're just entering the classroom right now, here's the URL to this virtual environment that you can see on the screen. You can type this into your browser address bar. And then when you go in there, there is a sign up process, very short and sweet. And then you'll need this token in order to enter the classroom. On the whiteboard, what I will be doing is maybe typing some commands that I want you to copy, like, okay. And then you'll be able to copy this and use this in your own environment. Then we also have these snippets here. It's more or less like the whiteboard. I can put some code here with the added value of this being syntax highlighted. Okay, echo hello. And of course, the most exciting part of this is here. This is your virtual machine. Each one of us gets a virtual machine provisioned on AWS, but that's just implementation detail. The interesting thing here is we all have an access to a Kubernetes cluster. Okay, right now you're seeing me doing this on my machine, but if you click on a similar button in your own browser, you'll go to your own machine and then you can run the commands on your machine. So each one of us gets a 3-node Kubernetes cluster. This is based on K3D. Anybody here using K3D? Okay, let's see what you're saying in the chat. No, okay, thank you. So, okay, only K3S. So basically, if you know what K3S is, then it's pretty easy. So K3S, as some of you know, and also related to the optimization topic, right? It's a very optimized Kubernetes distribution with all of the unnecessary code thrown out, all of the Kubernetes control plane components built into one binary, right? So we have the scheduler, the controller manager, and everything else in one binary. The database has been replaced with SQLite. Now that allows us to run Kubernetes in very low resource environments. And what K3D allows us to do is it wraps K3S and allows us to run a Kubernetes cluster based on containers. So basically, it's a system that allows us to quickly spin up and manage Kubernetes clusters, whereas each node is a container. So that's what happens here. We have an Ubuntu machine, and on top of that machine, we have a Kubernetes cluster that's implemented where each node is a container. If we run Docker PS here, we'll see that each one of these is actually a container, but we see them as a Kubernetes cluster. Now, this, of course, doesn't provide resource isolation. So all of these containers, they all share the same host machine resources, but it's good enough for what we are going to do today. And whatever is not possible in this environment, we'll just explain. Okay. So, okay, we don't need to run this here. If we weren't running, then we would have run the setup script and create the cluster. And we don't need to do this. So the only thing you actually need to do in order to, see that your cluster has been created is run kubectl get node. Just make sure you're getting access to the cluster because everything else has been set up for you. And yeah, the link to the slides. I promised you the link to the slides. So the slides are here. You can open them in a separate tab of your browser because it's easier to copy. If you want to copy stuff from the slides, it's easier to copy from there, from the HTML version than from the PDF version that we have here in the classroom. Okay. Now, there's one more thing I'd like you to do before we start. And that's, I'd like to introduce you to Perfect Scale. After all, I'm here because I represent Perfect Scale. Perfect Scale is a great service that allows you to connect your clusters for free. It's not open source, but we have a free community edition. Yeah, let's see what the chat says. You don't see the button for the terminal. It should look something like this, like a cloud with like a lab bottle in it. It should be underneath the snippet button on the left. It looks a little bit different than the one that looks in my screen. Mm-hmm. That's interesting. Okay. Evgeny. Suddenly, so somebody that I know, and I'm very happy to see him join my class. Okay, Vito, I can see you have a machine. I'm entering your machine right now
We
in my
found that it
environment.
was resolution based, pretty much.
Okay, because of the screen resolution. Okay. Okay. So once you zoomed out, you found the button. Okay. Cool. So yeah, back to what we're talking about. So what I'd like you to do is to introduce you to Perfect Scale. So basically, what we can do right now is everybody connect our clusters to Perfect Scale because this can be done for free. The only thing you need to do is go to, let me just log out. Go to perfectscale.io. Okay, here's the link. I'll put the link in stgo on the whiteboard. Okay, so please go to. Okay, once you're there, you can click on Get Started. Then there will be a sign-up process where you need to input an email. Now, free emails such as Gmail or Yahoo or what have you, or Hotmail, if you're using that for any reason, they won't work. we're filtering those out. So this needs to be a company email. Anything that looks like a company email, this can be a domain you own yourself. This will be also fine. So you need to input your name and company name, and then you'll be able to create an account. Okay, that's totally free, no credit card required. Okay, and once you're in, okay, this will send a verification email. So the only thing you need to take care of once you're in there is to approve the verification email to verify that you're an actual person. And once you're in there, you can input your email and your password, easy like that. And you're inside your account, and that's where you can add a cluster. So the first time you enter, you look at it will look like this. Disconnect this. You'll have this big add cluster button in the middle of your screen. Now, what we'll do right now, the first thing, okay, I'll give you a couple of more minutes because you'll probably need to take care of verification. We'll connect our clusters. Now, of course, this is not a must-have step in order to start optimizing whatever you're doing for Kubernetes. But I'd like you to do this so that in the end of this training, we can look at perfect scale and see how it makes the optimization flow for Kubernetes clusters much easier. Okay, so once you're in here and you have this button, actually, you know what? I'll give you a few more minutes. So again, go to perfectscale.io, create your account, and once you're in, you'll have the Add Cluster button. And while you're doing that, I'll talk a little bit more about Kubernetes optimization and the performance of Kubernetes workloads. Just, you know, the theoretical stuff that you probably know about, but it's good to have a common starting point so that we're all on the same page. Okay. So what we'll be looking at is optimizing the performance of applications running in a Kubernetes cluster. Kubernetes or not, application performance is impacted, first of all, by the code itself, right? The code can be more efficient, less efficient in its memory usage, the way it's built, what the stack depth is, how efficient the data structures is, how efficient the algorithm is. And of course, today we're talking usually about applications that have distributed pretty complex architectures. So the architecture is, of course, also very important in optimizing the performance of the application. We may be dependent on other components that are not performant enough. We need to implement caching and load balancing and scaling because everything is so distributed and we want everything to be very dynamic and to use the resources in an efficient way. And these things are not that easy to make happen. Okay. And of course, underneath it all, underneath the code efficiency and underneath the architectural concerns, in the end, this code needs to run on hardware, and that hardware provides us resources, and these resources need to be available, right? We need to enable access to storage. The storage needs to be performant. We need to have wide enough network bandwidth. We need to provide CPU time. The CPU needs to be available, and of course, memory. And this is finally related to Kubernetes because before that, you know, the code is not related to Kubernetes itself. The architecture is created in the architecture's head, and it may be aware of being executed on Kubernetes and may use certain Kubernetes constructs, but Kubernetes doesn't impact that directly. Once we're on Kubernetes and we're running stuff on Kubernetes, Kubernetes gives us the necessary tweaks and knobs that allow us to optimize whatever we've built before coming to Kubernetes. Okay, a little bit, to get us all on the same page, how this stuff, the infrastructure resources can be optimized in Kubernetes, and we're not talking about everything in today's workshop. So first of all, storage. We have the container image storage. In order to optimize that, we can and should, first of all, optimize the images themselves. We want the images to be as lightweight as possible. So for that, one of recommended approaches is using images that only bring whatever is necessary. Google's distroless project gives us very lean base images for most popular application stacks out there. And of course, you can also build your images totally from scratch. Okay, cool.
Let's go.
So what I was saying is, and thank you for letting me know you lost sound. Okay, we can optimize container. We can pre-pull container images. There is also a new initiative about OCI image caching that I only heard about last week. So definitely look into that. So this is for container images. Of course, the other area of storage is the ephemeral volumes, managing, the local volumes, the remote volumes, and persistent volume management. We'll say a few words about the ephemeral volumes. We're not going into persistent volumes today. It's a topic in itself, not touching that today. Regarding networking, the default kube proxy relies on IP tables. It's not particularly fast. It's probably good enough for you unless you're doing something that really requires very high bandwidth, like, I don't know, video streaming or gaming. If necessary, there are alternatives to kubeproxy, for example, kuberouter. Kuberouter by default uses IPVS instead of IP tables, which is a different routing technology inside the Linux kernel. It's more performant than IP tables. You can tell kubeproxy, by the way, to use IPVS, or you can just totally replace it with kuberouter, which uses IPVS by default, and kuberouter can also perform other stuff. So basically, it can be your whole CNI solution, and then it's more efficient, but it's not as battle-tested as kubeproxy, so definitely check if this fits all of your needs before going that path. You can also use kubeproxy with NF tables because IP tables are actually on their way to being deprecated, and NF tables are more performant, but again, still not very widely used. And of course, there's always the option of replacing kubeproxy with something like Cilium or Calico based on eBPF and improving the performance this way. Here's a benchmark that was done in 2021 by Cilium that shows that they both perform better than kubeproxy, but they were tested in comparison to IP tables. It's not sure if, for example, they also provide much better performance than using kubeproxy or kuberouter with IPVS or NF tables. Okay, additional considerations, of course, what impacts our networking performance is the distance between our pods. So definitely use scheduling constraints in order to avoid noisy neighbors effect, and consider switching to topology-aware routing or adding topology-aware routing to your deployments that has been in beta since version 1.24 to improve latency, to make sure one pod that needs to talk to another pod talks to the pod that's next to it and not to the pod that's located in another availability zone. Okay, that was for the stuff that we're not covering today, right? So we talked a little bit about storage and about networking. Let's now talk about CPU and memory, which are the resources that we're actually talking about today. So, which can be considered, as runtime resources. So first of all, how do we measure? In order to optimize anything, we need to be able to measure it. Resource allocation and consumption on Kubernetes is collected and exposed via the so-called metrics pipeline, which consists of, first of all, the C advisor, which is the daemon for collecting the metrics that runs inside the kubelet binary. The kubelet then exposes the metrics through its own API called metrics resource and stats. And finally, we can install a component called metrics server in the cluster so that we can collect this data from all of the kubelets and expose part of the data for other components to be able to use it. Okay, so let's first of all, okay, and that's the first time we're starting to run something. Coming back, okay, first thing first, okay, wait with this for a second. Let's hopefully you're now, okay, I see we have more people. So hopefully, okay, let me go back here. If you haven't done so yet, go to perfectscale.io, click on Get Started, sign up, and once you're signed up, you go to this screen and you click on Add Cluster. Okay, the first thing you need to do is, of course, add the PerfectScale Helm repo. And this is a generic command, so I can definitely paste it here for you so that you can all execute it. Okay, and I see that the first thing I forgot to do is install Helm here. So we'll just use snap the way it's recommended. So even before that. Okay, so let's install Helm in our environments. Okay, and then we'll do Helm repo add perfect scale. Now, once you've done that, you go back to the perfect scale environment. You give your cluster a name. I'll call mine build stuff, probably, because we're at this wonderful conference here. This is where you choose the optimization policy for your cluster. We recommend starting with balanced before you know anything else that you want to do. This will allow you to generate the Helm installation command with a unique secret that will allow PerfectScale to uniquely identify your cluster and connect it to your tenant. Okay, scroll a little bit further to copy this command to clipboard. Go back to our cluster and run the Helm command. And of course, this command is unique to every one of you because this has the client ID and client secret in it. This goes and installs the PerfectScale agent in our cluster. Now, a few words about what a PerfectScale agent is. It's basically a very lean agent written in Go that collects all of the utilization, resource utilization metrics from all of the pods and all of the workloads running in a cluster. And once they're collected, it gets sent to the PerfectScale backend, where we run our own data pipelines that allow us to provide the recommendations and also further to automate the resource allocation for the cluster in order to keep it continuously optimized. Now, we'll allow this thing to run a little bit. We, of course, need to collect some information in order to start optimizing anything. So we'll just leave it running and continue with our workshop. So back to our workshop. Let's run this. So what this does, as I said, all of the C advisor metrics are basically available as they are through the Kubernetes API. So what this command does is we're getting the name of the first node in our cluster. and then we're getting the raw cAdvisor metrics from that node. Let's see what we get. And I'll put this on the whiteboard for you so that you can run it. Okay, so we've installed Perfect Scale so that we can see in the end how well our optimization effort is going. And then we run these commands in order to look at the cAdvisor metrics. And we can see that basically what cAdvisor does is expose a lot of the container metrics in that standard Prometheus metric format. We have like the swap bytes, the NVM capacity, the CPU physical cores, the container threads, etc., etc., etc. A lot of metrics. Much more than we usually look at, much more than we usually use, but definitely many of the metrics that can be useful for our optimization effort further on. Okay, so we do have the metrics. They come from each one of the nodes. Now, what if we don't really care about the nodes right now? We do want to get all of the information about the pods without knowing which nodes they run on. And we want to enable ourselves and our users to see these metrics within the cluster. We could, of course, collect all of the metrics from the kubelets and send them to an external observability solution like Datadog or New Relic. We can use a self-hosted solution like Prometheus. Or instead of all this, we can use metrics server. So why would we want to use metrics server? So the pros of metrics server is it's very lightweight. It's much easier to install it than even Prometheus or even Victoria metrics for that reason. It doesn't require us to define any storage or database, and it's already used by the Kubernetes native autoscaling. So if you want your horizontal pod autoscaler to work, you need metrics server in place. And of course, it also has its cons. It doesn't have any data retention. It's only exposing the CPU and RAM of nodes and pods. It doesn't report anything about the storage or network or whatever. But in most cases, it's not needed for what it's supposed to do. So it's also fine. We may install something fancier later, like Prometheus with Grafana, but metrics server works very fast. It doesn't use almost any resources. It's required for autoscaling anyway, as I said. And another great thing is it comes pre-installed in K3D. So we don't need to run these commands. It's already installed there. And once it's installed, we can, of course, use it by using the kubectl built-in command, kubectl top. We can do kubectl top nodes and kubectl top pods, and this will show us the resource allocation and utilization of pods and nodes. Okay, this is for nodes. For pods, I'm getting no resources found in default namespace, but I can do, of course, kubectl pod -a, and then it will show me the resource utilization for the pods running in kube system and also for the perfect scale agent. Okay, this is all pretty common knowledge. Now, the way the metrics server exposes the metrics is through Kubernetes API aggregation layer, which basically means that the metrics become available through APIs metrics kubernetes.io. Let's run this just to see the way they're exposed when we don't run kubectl top. think this will work. Let's see. Okay. Just a second. Copy pasting didn't work for me, at least not for me. Okay, this should be okay. I'm missing a space. Okay, so this works. So we can see this is exposed in JSON. We have all of the usage for CPU and memory. It shows us the timestamp when these metrics for node has been exposed. This is similar to what we get in kubectl top node, and there is another API for pods, of course, that we can also use. Okay, regarding the usage that we're seeing is one notice is that the RAM usage that we see should correspond more or less to the resident set size. So whatever is used by our process with all of the variables it gets allocated. Our pods will also need some extra space for stuff like buffers and caches. And in general, on modern Linux systems, there is actually no free memory, right? So whatever is not used by the processes is used by the kernel for caching, but can be immediately released whenever the processes need it. And still, this memory is needed, so we never aim for 100% memory usage. Okay, so metric server is the very basics. We will usually have it in the cluster. We don't have to. For example, the Perfect Kill agent doesn't require to have metric server installed, but it's a nice utility tool. And again, as I said, once you want to use the horizontal pod Autoscaler, you need to have the metric server, or you need something else to implement the API aggregation layer that the metric server is relying upon. There are other tools like Kube Capacity and Kube Resource Report. Definitely look at those in your free time. Okay, let's see, we have a message here. Yeah, thank you, Vito. I noticed that. I need that space. Okay. So this is the metrics pipeline. Let's talk a little bit about the resource allocation in Kubernetes. So, of course, in order to manage how much resources our containers get access to, we can attach resource indications to our pods. We can specify limits and requests. These can be defined for CPU and or memory and or ephemeral storage. Now, if we're using GPU, for example, for running language models, then we can also define GPU resources, and that is also only applicable for limits, not for requests, using device plugins. And we need to install these device plugins on our cluster, of course. And there is support for allocating additional resources, GPUs included, which is on the way through that thing called dynamic resource allocation, DRA. Not looking into that today, and it's still not anywhere near to production readiness. So definitely, if you're interested, look into that in your spare time. Requests are guaranteed reservations of resources. Requests are used by the scheduler in order to understand where to send our pods, because it looks at how much the pod is requesting, it looks at the nodes, and whichever node has enough resources that are requested by all of the containers in the pod, the scheduler will schedule the pod onto. A node cannot be overcommitted with requests. And of course, a small amount of resources is set aside for system components. So this is the node overhead. Limits, on the other hand, are hard limits. A container cannot exceed its limits. And there's a difference between, of course, the limit of the CPU and the memory, because CPU is and storage and ephemeral storage. So out of all these, CPU is a compressible resource. We can easily take some CPU from a process, and that won't corrupt the process. It will just make it run slower, which is called throttling. So a container that exceeds its CPU limit is throttled, while a container exceeding its memory limit is killed instantly, because we cannot easily take a memory from a running process. And of course, a container exceeding its disk limit is also killed, but that doesn't happen instantly, because the kubelet checks that disk usage periodically by the kubelet, and it takes it a couple of minutes to identify this and then go and kill that container. And of course, limits can be over provisioned, because the schedule is not looking at limits, but once a container is crossing the limit, then it starts doing something about it. The kubelet starts doing something about it. Okay, let's check the resources we have already allocated in our cluster by running this command. So we'll take out all of the pods in JSON, and then we'll filter that through with JQ. Delete these commands, erase them. Put this on the whiteboard for you. Okay, so what we're doing here, this a little bit, we're looking at all of our pods, getting their definitions in JSON, and then running this JQ query on them in order to find, for each pod name, all of the container resources that it defines. Okay, and this is what we have here. So we have 3 pods actually. The core DNS has definitions for memory limit and CPU and memory requests. The local path provisioner doesn't have any resources defined. The metrics server also has actually has only requests defined, and perfect scale agent. First of all, we can see that perfect scale defines, installs the kubestate metrics pod, which has requests defined, and the agent itself is also defining requests, but not limits. Okay, so this is what we have here. Okay, CPUs are expressed in virtual CPUs. This can be integer values, or we can specify them in decimal values, or we can also specify them in millicores, and that's something that's most prominent. That's what you see in most specs. Memory and ephemeral disk storage are expressed in bytes, and of course they can have the KMGT suffixes. And you can also express them in not only in megabytes and kilobytes, but also in mebibytes and kibibytes. Okay, this is what a spec with resources looks like. Again, nothing new here. Maybe beside the ephemeral storage that I'm not sure any of you are using. So if you are using ephemeral storage requests and limits for your containers, definitely send a plus to the chat, just to, because that's interesting. I know not too many folks use that. Okay, as I said, CPU is compressible, memory is incompressible. By the way, how do we, if we're not on Kubernetes and we still want to allow a process to run even when it runs out of memory, what do we usually do? Okay, so the answer is we usually are able to swap out the memory, right? Now on Kubernetes, swap is not enabled, and we'll talk about that in a moment. But first, let's talk about CPU. So when a container runs low on CPU, basically why that would happen, right? Either we've defined the CPU limit and container is hitting its CPU limit, or all CPUs on the node are at 100% utilization, right? The result of that is that the application that's in the container will run slower, it would get throttled, but there are no other consequences. So latency will be slower, our customers maybe will be less happy, but beside that, it's okay, kinda. Now, how are CPU limits implemented? So basically, a container with a limit will get rationed by the kernel, and we'll see that in a moment. And this ration will be measured each period that's defined by kernel setting called CFS period US. So each such period, by default, 100 milliseconds, it will get a CPU quota, like an allowance that based on the limit that we've defined for it. Once it has used its quota, it will wait until the next period comes. If it hasn't used it, it won't be stalled, right? And this can easily result in throttling for workloads that are bursty, that can be sleeping one moment and then suddenly need a lot of CPU. Like in the example here, there's a web service that receives 1 request per minute. Each request takes 1 second of CPU. Average load is 1.66%. And let's say we set a CPU limit of 10%. That means that every 10 milliseconds, every 100 milliseconds, we'll get a quota of 10 milliseconds. And that means that obtaining that quota for full 1 second of CPU will take 10 seconds. So we'll need to wait each time that we need more CPU. And that means that the observed latency for the request will be 10 seconds instead of 1 second that we actually suppose that it should take. Of course, in real life, the scenarios will be less extreme, but they definitely do happen. Now, this problem gets even worse when we have multi-cores, because each core gets a small share of the container CPU quota, and the kernel distributes that quota to different CPUs. And if we allow that quota and the container process uses up its CPU quota for the local CPU, it waits before returning its quota back to the scheduler. And that means that again, this query stays on the local CPU because it can be useful, because if the thread wakes up again, it may need to use it, but if it's not used, then it's just wasted. Okay, so the CPU waste becomes even worse on CPUs on machines with multiple cores. Basically, that means that if you run small and bursty workloads on machines with multiple cores, this may lead to a lot of CPU waste. In order to understand if this is happening, definitely check the throttling parameters, and most Kubernetes observability solutions are measuring this and also are alerting us about this. A solution to this is, first of all, either to be generous with the CPU limits or even not set them at all. There is a long discussion on the internet about if we should even set CPU limits, and the very simple reply to that would be, don't set CPU limits if you want maximum performance. Do set CPU limits if you want your workloads to behave in a predictable way. Okay, also the kernel needs to have appropriate patch level. There's a link to that. And also Kubernetes allows us to use static CPU manager policy, which allows us to lock a container to a specific CPU. So if we need to make sure that our container gives us predictable behavior, and it has access to one specific CPU. Of course, it's not very efficient because we're not getting maximum efficiency and maximum performance, maximum utilization, but we do get great performance for that specific container. So definitely look into that too. Okay, let's look at CPU limits. Enough talking. Let's create a deployment. Okay, and I'll put the commands on the screen for you because it's really not easy to copy it from here. Okay, I want to go to slide 58 here. And I'll copy the command from here. And I'll put it on the whiteboard. Okay, we'll create a deployment now. We'll use a small Flask web application that's called Busy HTTP. It was originally written by Jerome Petazzoni and then expanded by me. What it does is basically it has a number of endpoints. The very basic endpoint sleeps, it takes one CPU core and sleeps on that CPU core for 1 second. So basically it occupies the CPU. And it also has an endpoint for allocating and freeing memory, but we'll probably look into that later. So what we're doing here is we're running this command in order to create a deployment YAML file. We're running kubectl create deployment in dry run mode, which only gives us the YAML specification for the deployment. We're writing that to a file, and then we'll edit that file in order to allocate the resources. Okay, so that. Now we'll open the deployment YAML file. So about editing files, you have VI installed here. If you're not comfortable with VI for any reason, there is also Nano. And in addition, there is a button on top of your virtual machine console, and it's called editor, I think, and then that allows you to access all of the files in your machine file system, and you can go through that, and you have like kind of a graphical editor inside your browser. So use any of those. I'll use VI. I'll open the file. I'll go to the resource stanza, and I'll replace it with what the slide has. And it's this. So put it here. I'll create a snippet right now, which will be YAML snippet. And we'll set requests and limits for the CPU to the same amount, which is 50 millicores. It's here. And of course, in order for this to get pasted correctly, I need to do set paste in my VI. If you're not in VI, you don't care. It didn't work too well too. Okay, fix the indentation then. I think I'm fine. Okay, and now let's apply that. So going to the next slide, once we've fixed the deployment YAML, actually, you know what? I'll put the whole deployment YAML on the snippet for you so that you can just use that whole thing. Just that. Okay. And we'll kubectl apply it. And once we've applied it, we'll also create a service for it by using kubectl expose. The service is exposed on port 80. Expose it. Okay, let's check that our pod is running. Okay, the pod is actually running. Now, what I'd like you to do is, first of all, to run kubectl top on that pod in order to see its utilization. In order to do that, in your stgo environment, you can click on that little plus on top of your console window, and it will open an additional shell. And you can run that command in your additional shell. So we'll run a watch with an interval of half a second on the kubectl top pod command. Okay, this in a separate shell. Okay. And in addition, we also want to look at the cAdvisor metrics. Working very good, so I'll copy it here. Okay. So I'll put the command here on the whiteboard again. In yet another shell, okay, we'll run this. What we're doing here is we're finding that pod, we're finding the node that it runs upon, and then we're extracting the metrics for that node for the cAdvisor. And we're looking for the throttling metric in that node because we want to see how throttling occurs for that specific container. So really see the throttling happening in real life. Okay, and here are the metrics. We can say, first of all, okay, right now our pod is not doing anything. It's a service that is not getting any requests. We allocated 50 millicores of CPU for it. It's only using 1 millicore. If we'd run watch earlier, we'd probably see that there is this initialization that's happening, and that's very usual, for Python and also for Java. When the program comes up, the interpreter needs more CPU in order to load everything. So you'll see CPU jump in the beginning. So you would have seen probably something like 30 millicores of CPU in the beginning. But right now it's not using any CPU. And yet when you look at the throttling metric, you'll see that it's already getting throttled. Not very hard, like this is the amount of seconds it's been throttled out of this whole amount of seconds that it has access to, that the CPU allows it to access, but it's already getting throttled, even though it's not doing anything, right? And we'll now run a test on it in order for it to do access the CPU, and we'll see how severe the throttling becomes. So in order to do that, we'll run a tester container based on a little image that's an Alpine container that has all kind of network utilities installed in it. So let's run that. Okay, so we're running this container, this pod called tester. Inside of it, there is one container based on this image, and we're running it with a ping to localhost in order for it to be available for us. Okay. Okay, so the pod is there, and we will now go into that tester container And once we're in there, we'll do a small benchmark using the AB tool. So we'll go into the container. Once we're in there, we'll go into the container. Okay. Here we are in the container called tester, right? And in there, what we do is we run a benchmark. So we're accessing the service named busy on its CPU endpoint. And we're also telling it to load 2 CPUs for each request. So basically what it does is it uses Python's multiprocessing in order to run the requests on both of the CPUs. So we're telling it to load as much CPU as possible. Let's run the test. Now, what AB does, it provides us these parameters here. So basically, this is the concurrency. So we're saying, I want you to send 20 requests in 20 concurrent threads. So basically, imitating 20 clients, sending 20 requests. Okay, and we know that each request is going to take a second to return. So we're supposing that this test should take about 20 seconds. Okay, this says benchmarking, busy, be patient. And while the test is running, we'll go and look at what happens with our metrics. Okay, so we see that first of all, the CPU starts getting loaded. And after a while, it'll get loaded much more. And of course, the watch is getting refreshed only half a second, and it takes time for the metrics server to report the metrics. It doesn't report them immediately because it takes time for it to go and collect them from the kubelet and then expose them through the metrics aggregation layer. So we will see a boost in the CPU usage, probably not a huge one. But when we go back here, we'll see that, of course, the throttling metric has become much higher. So we will see a lot of throttling occurring here for the pod. And then eventually this will go down, okay? And when we look at the benchmark results, we'll see that this benchmark at its total has taken, the longest request has taken 25 seconds, right? And this was the mean, right? So this is the performance right now. Let's now compare that to unsetting the CPU limits and doing the same benchmark, okay? Because that's basically what we want to do. We want to make sure that the CPU limits are working and to understand how they are working. So I'll probably go out of here. I'll edit my deployment YAML. I'll remove the CPU limits. Again, this is for us to see the CPU limits in action. Okay, I've edited the deployment. I'll apply it again. I will now go back to watching my pods. Of course, the pod gets replaced and it takes time for the metrics server to expose the metrics for the newly created pod. And by the way, when you look at this now, you'll see that little jump in CPU that occurs in the pod when it gets created. For example, when you look at this in the perfect scale interface, and we'll take a look at it later, perfect scale will tell you init observed, because it does realize that these interpreted languages, they always have that CPU init happening, and it may be much more severe for larger applications. This is a very small application. Okay, and once we've done that, well, first of all, when we go back here, we'll realize that now there is no throttling occurring, right? So this query for throttling metrics is not returning anything because once we don't have limits, there's no reason to throttle processes unless we're out of CPU at all, but that's not what's happening. Okay, now let's go back to running that same benchmark again. Now we'll see that this time, of course, the CPU usage for that container goes up. First of all, to around 650 millicores, and then further closer to 2 millicores. So basically, what now our container is trying to do is occupy both CPU cores that we have on this machine, because it can, right? And of course, no throttling is occurring. And when we now look at our results, we can see that, of course, this impacts the performance, right? So we're now here for the longest request, and we're here for the mean. Comparing that to the previous benchmark, we can see that this was our longest and this was our mean, so definitely performance impact can be easily seen. Okay, now here's a question. What happens if we do set the CPU limit to 2, which is the number of CPUs available on this machine? Will throttling occur or not? Because this is, the maximum CPUs. Basically, it means as if we're not setting any limit. And the response to that is that we'll see much less throttling, of course, but it will occur. Because the moment you set CPU limits, the kernel starts rationing our processes, and that means throttling can occur even when there is available CPU on the machine. And that's why if you want most performance out of the resources you have, the recommendation is to not set CPU limits, because setting CPU limits even to very high quantities will still lead to throttling in many cases. Okay, this was CPU limits. Let's delete our pods and deployments and go on to our next topic, and that will be memory. Of course, we'll need to exit the tester pod. And delete all of our pods and deployments. Okay, so what happens when we run low on memory? Usually when the kernel runs low on memory, it starts to reclaim used memory, and it has the following options. It can free up some buffers and caches. It's the easiest and the fastest. It might affect performance if cache memory becomes very low, but it doesn't corrupt processes. Option 2 would be to swap out the memory for the processes that use a lot of memory, which means basically take some memory from the process and write it to disk, and then give it to another process that is currently starving for memory. This can have a huge negative impact on performance because disks are slow. Writing to the disk is slow, then coming back to that memory and reading it from disk is also slow. So that process that the memory is taken from and swapped out from will get a heavy impact on its performance. And of course, option 3 is not do any games with memory, just kill a process and take all of its memory. Okay, and that's the out of memory or out-of-memory killer in Linux. Kubernetes used to have no support for swap at all. Since version 1.28, there is a limited swap memory support available. With no swap available, which is the default, if a container exceeds its memory limit, it gets out of memory killed. And if node memory usage gets too high, it will immediately kill the containers and evict some pods because the node is under pressure. Okay, enough talking. Let's see some kill in action because that's fun, of course. So we'll apply this YAML that we have in our environment. I hope that it works. Okay, let's see. Huh. Just a second. Okay, I think there is one thing here that's happening. We need to go into this directory and do a git pull. Okay, yeah, it's not up to date. So yes, before we do that, okay, so first of all, let's go to and do a git pull. Okay. Otherwise, it's not going to work. And once you've done that, you can run this, hopefully. Let's see if this command works for me. It will work for you. Yeah, this is better. So I'll put it on the whiteboard for you too. Now, what is going to happen, hopefully faster than slower, is that the container gets created, then it gets running, and then it goes into killed quite immediately. And of course, then goes into crash loop back. And the example, the explanation for that is this runs that same Python Flask based web application that requires around 40 megabytes to run, actually a little bit more than 30, if I remember correctly, but it has a memory limit of 20 megabytes defined in the YAML that we just deployed, and that means it will continue to get killed and restarted. We'll fix this issue later. Now, finally, what happens when we run low on disk? When the qubit runs low on disk, it starts to reclaim disk space. It's quite similar to what the kernel does, but it has its own categories. So option 1, it can garbage collect dead pods and containers. No consequence for the running processes, but the logs will be deleted, and that's why we don't usually rely on having the logs stored on the nodes, and we usually want to store them somewhere else. Option 2 would be to remove unused images. Again, no consequences, but we'll need to repull these images if we need them later again. And finally, option 3 is to evict pods and then remove their containers from the node in order to reclaim their disk usage. Now, this only applies to ephemeral storage, not to persistent volumes. The ephemeral storage includes the read-write layers of the containers, the volumes that are of type empty-dir, and the container logs that are stored on the node. It doesn't include the container image or other types of volumes, such as host path or local volumes. what enforces the disk usage is the kubelet. There can be a small delay before pod termination, and we'll see this in a moment. Now, it's also possible to separate the nodefs and imagefs treatment for the kubelet, and that's kubelet initialization config. Nodefs is the main file system of the node. For example, empty tier volumes and container logs are in that part of the file system. And optionally, you can also configure the container engine to use imagefs, and then that will be a separate file system part reserved for images. Then its disk usage is tracked independently, and if its usage gets too high, it will remove the old images without impacting the nodefs. Okay, let's see the ephemeral storage limit in action. So I have an example for that too here. Let's run that. Okay, exit the get pod here and run this. And while we're doing that, let's look at that. This YAML. Okay, so go back here. I don't want this watch anymore. I want to look at this YAML. So basically what this does is it creates a pod. In that pod, it creates a volume named my volume that's based on an empty tier. This has a size limit of 500 megabytes. But that's not what matters. What actually matters is the resource limits of the container. So the container says, I'm mounting this volume on a path test. I'm then running DD in order to write to disk. Now this is only writing to the internal storage layer of the container. And we have this limit on ephemeral storage here of 100 kilobytes. And if we go back to looking at that container, we'll see that after about 30 seconds, this causes the pod to error out. And when we look at kubectl describe pod with volume, we'll see pod ephemeral local storage usage exceeds the total limit of container of 100 kilobytes. And then what happens is it does stopping the container. It takes a little bit of time for the container to stop. It says container runtime didn't kill the pod within specified grace period. And then finally, the container does get errored out. Okay. So how does all that work? So Kubernetes passes the resource request and limits to the container engine. The container engine applies this request and limit with specific mechanisms. On Linux, this is typically done with control groups or cgroups. Most systems use cgroups v1, but cgroups v2 are slowly being rolled out. In v2, we have new interesting features for memory control, like, for example, ability to set actual requests in the cgroups. So to actually reserve memory for the process. Before that, it wasn't happening. So even though the scheduler would make sure that there is enough memory on the node at the time of scheduling, that memory wouldn't stay reserved. So that would probably make it possible for other processes to take that memory, and that memory won't be reserved for the process. In cgroups v2, we can actually reserve the memory requests to the process. And there is a post that I wrote about half a year ago that dives deeper into how cgroups v2 impact your Kubernetes deployments. The link doesn't work here in stgo, but if you go to that slide 71 online, and the slides are available to you, by the way, even after the training. So definitely, yes, use that. If you want a deeper dive into C groups, V2. And also, yeah, C groups V2 also allows us to define swap per process group. And kubelet also allows us access to that. So if you do decide to enable swap, you can enable it for a specific container. Again, if you need this, if you want to dive into this, definitely look into it. Okay, it is possible to enable swap. That's what I'm trying to say. But it can impact your performance. Okay, so once we've defined or haven't defined our requests and limits, what that impacts for our container, beside it getting throttled or killed when it reaches its limits. For example, if we don't define limits, if we just define the request, it also impacts our pod. Basically, what it impacts is its quality of service. So each pod is assigned a quality of service class, visible when we look at the pod in its status quality of service class. So let's look into that. Okay, we have two pods here, right? In this default namespace. Let's look at one of them, get pod. Let's look at BZHTTP, right? And we'll do, I want its output in YAML. And when we look at its status here, in the end, we'll see that its QoS class is burstable. Okay, what does that mean? If limits equal the requests for all of the containers in that pod, that means that its quality of service class is defined as guaranteed. That means as long as the container uses less or equal to the limit, it won't be affected. Okay, so that container is guaranteed to get the resources it needs. If the requests are set lower than the limits, which is what we often do, the quality of service class is called burstable. That means the container is promised some amount of resources when it gets scheduled. Again, quite a lie if we're talking about memory, because C groups V1 were not actually reserving that memory for container, only reserving the CPU. But yeah, it's kind of promised to have access to these resources, but it's also allowed to get access to more resources. And finally, if we're not defining anything, then the QoS for that container, the quality of service, is defined best effort. What that impacts, when the node is overloaded, best effort pods are getting killed first. Then we are killing burstable pods that are over the requests. And if burstable and guaranteed pods are below the request, they're never killed unless if the node is failing. Okay, and if you only use guaranteed pods, no pods should ever be killed as long as they stay within their limits. Okay, let's fix the memory allocation for the BZHTTP pod. We'll open this scripts kill YAML. Where am I? Okay. We'll fix the memory, boost it to 40 megabytes. And we'll redeploy that. kubectl apply -f scripts kill. Of course, we need to type apply correctly. And I'm not allowed to do that. Or am I? Okay. And of course, the slide gives me the answer to that. So in general, the resources currently are immutable for pods. Why is that? Because it's not possible to change the resources without replacing the container, without killing the container, starting a new one. Still not possible. Actually, there is a feature called in-place pod replacement, resizing, sorry, that's available in alpha since version 130 or 128, actually, I think. And it's supposed to go into beta, I think, sometimes and maybe next year. But it's been a long time in the making. I can send you the link to the enhancement proposal that takes care of that. And I also actually have a blog post about this. But right now it's not possible. So if you do want to apply your resource changes to a running pod, you need to add minus minus force, and then that will allow it to apply and force the restart of the container. Okay, let's look at the pod. And see that it's not out anymore. And we'll also check its status QoS class. Okay, and we see that the pod is burstable. It's not the right view. Okay, and it shows us the status QoS class. Okay. Now, what if we don't define anything? So basically, if we don't specify a request, but only a limit, then the request will be set to the limit by the API. If we specify a request without a limit, then there will be no limit, which means that the limit will be the size of the node. And if we don't specify another request or limit, then the request is 0 and the limit is the size of the node, which is not something we usually want. So we want to set our own default values. How do we define these resource values? Because again, if we're not setting any resource values, that means our cluster is very far from being optimized. That means most of our containers are probably over provisioned. They're getting access to as many resources as they need, but on the other hand, they may be scheduled to a node that doesn't have enough resources for them to run, so they can also probably be under provisioned when they actually need these resources. So under provisioning means no reliability because stuff can fail because it doesn't have access to enough resources, and over provisioning is of course very wasteful because we're paying for resources and not actually using them. Generally, that's not what we want. Absolutely not in production. So how can we set these resources? How do we even know how much resources our containers need? Or maybe a question to you. How do you set resources for the containers that you're running in your clusters? Now, the reply to this is usually, in most cases, is that there is a lot of guesswork there because, you know, the developers have no idea what happens in the production clusters. On the other hand, the ops people who are responsible for the clusters and for the infrastructure resources, they have no idea what the code is doing and how much resources it needs. So there's a lot of guesswork. And sometimes, you know, at least in the beginning, the developers just give up and don't set up any resources, or I don't know, write something that they think that probably is close to reality. We can, of course, do this manually for each container. It's simple. It may be effective if we know what we're doing, but this is, of course, tedious. We can do this automatically by using something like a vertical pod autoscaler that we'll look at a little bit later today. It has its own issues. We can do it semi-automatically, start with a tool like PerfectScale that provides you the recommendations and then allows you to switch to automation once you learn to trust the tool. And we can also set some defaults by creating limit ranges. And that's what we're going to look at right now. Okay, so what we can do is we can create limit range objects to indicate any combination of minimum and maximum resources allowed per pod, defining default resource limits, resource requests, and of course, by this, we can also define the maximal burst ratio, which is the delta between the request and the limits. The limit range objects are namespaced, and they only apply to their own namespace. Here is what a limit range object looks like. So they only apply to that container type right now. It's not possible to apply limit ranges to whole pods. So for each container, it will define like the minimum CPU, for example, is 100 millicores and maximum is 2000 millicores or 2 cores. And it will also define the maximum for memory. And it will also define the defaults. So it will define those for limits, and we can also define the default requests. So this, for example, defines that the default CPU request is 500 millicores, and also the default limit is 500 millicores, which makes this container guaranteed for CPU. Okay, so when do limit range restrictions go into action? They're enforced only when a pod is created. Basically, a limit range is a mutation and validation admission hook. That means that if there are some pods already running, the limit range is only applied after they became running, after they started existing in the cluster, the changes won't be applied. The limit ranges don't prevent creations of invalid deployments with specs that defined invalid pods, but that means that afterwards, the pods for these deployments or daemon sets or stateful sets or whatever type of workload you're defining won't get created. If there are multiple limit range restrictions, they will all apply together. And if a limit range specifies a max for resources but no default, that max value becomes the default too. Okay, let's look at how this works. So we'll create a limit range by using a script that we have in our repository. This. So that's what we'll do. First of all, we'll create a limit range. Okay. Now we'll run a simple Nginx pod without defining any resource requests or limits for it. And now we'll look at the resources that got applied to that pod without us needing to define them. I'm giving you the commands so that you can easily run them in your own environment. Okay, and we can see that even though we didn't define anything for that pod, we just ran a pod. It now has the limit of memory set to 250 megabytes, and its requests set to 500 millicores of CPU and 150 megabytes of memory. right? And we can see that this comes from the limit range. If I do now kubectl get limit ranges, some CPU, some mem, let's describe it. We'll see that it sets the default request for memory to 150 megabytes, the CPU request for 500 millicores, and the limit. So these are exactly the requests and limits that got applied to that pod. Okay, let's delete the pod. So when we don't define anything, the limit range sets the request and limits for us. Now, let's see what happens when we try to create a pod and we do set limits and requests for it, but they don't comply with what the limit range defines. Okay, what we'll now do, we'll create an additional limit range that sets the minimum and the maximum values. So we're creating that limit range and then we're looking at it. And when we look at it, it says, I'm now defining the minimum container CPU limit to 200 millicores and the minimum container memory to 150 megabytes. And I'm also defining maximums. And I'm defining the default requests and default limits. Now what we'll do is we'll install Nginx, but this time we'll install it with a Helm chart. Now the Nginx Helm chart that comes from Bitnami allows us to set the resources for the Nginx pod by providing some presets. And there's this preset called Nano that gives a little requests for memory and CPU to the pod that gets created. So let's see how this works. Okay. Now let's see if the pod got created. I'm saying I want to find the pod that has this label that I know that the chart applies to it, which is app Kubernetes IO /name Nginx. And when I try to do it, it says no resources found in default namespace. And when I do kubectl get all, I'll see that there is this replica set Nginx that says that its desired amount of replicas is 1, but its current and ready are 0. So where is our pod? Let's look into this. We'll do describe on that replica set to understand what's happening. Now what we'll see here is it says error creating pods is forbidden. Minimum memory used per container is 150 megabytes, but the request is 128 megabytes. And minimum CPU used per container is 200 millicores, but request is 100 millicores. So basically what it says is the limit range defines the minimums, but what the actual container requested is less than the minimum, and that's why I'm refusing to create this container. It's requesting too little resources. It's supposed to be requesting more. How can this be fixed? Well, one option is, of course, complying with the limit range and setting the requests higher. But if we don't want to do that, if we're saying the limit range is bogus, then we can just delete the limit range. Called min-max. Now that won't lead to the replica set immediately creating the pod. So if we look at the replica set, actually it happened quite immediately, but when we do describe, let's see. Yeah, okay. It finally it tries to create the pod all of the time, and yeah, it does these checks. Actually every second. So the moment it finds out that the limit range is not in its way anymore, then it immediately creates that pod. Interesting. I guess this is related to a different Kubernetes version that I was testing this with, because this says it takes approximately 5 minutes until the replica set to reconcile, but this replica set is actually reconciling in seconds. Okay, not something I expected, but this is the way it works. Let's delete the Nginx chart and continue. This. Nginx. By the way, almost all we're doing here is possible to do on Killer Coda. If you haven't used Killer Coda in your life, then definitely do yourself a favor and go get acquainted with it. It's right here. So this provides you with temporary Kubernetes environments. Each one of them, if you're using the free version, is giving you access to a Kubernetes playground that's available for 1 hour, and you definitely can use my examples in my workshop and run them here, and most of them will pretty surely work. Okay, let's continue. How much time do we have? Okay, we have another like half an hour, a little bit more. Okay, we won't touch too much about namespace quotas. So in addition to limit ranges, we can also set quotas per namespace, which apply not to specific containers and how much resources they are getting, but the total usage in a namespace. So we can say, for example, this namespace, all of the pods in that namespace, all of the containers in all of the pods in that namespace can have access to a maximum of, I don't know, 30 CPUs. And then this quota is spread out on all of the nodes that all of the pods in this namespace are running. And this is another way to optimize resource utilization, especially if we have different products running on the same cluster in different namespace, or different teams using different namespace, and we want to budget their resource utilization. This is another way to manage this. Want to look into this more. Definitely look into this, but we don't have time for this right now. Now, the quotas can apply to just all of the pods in the namespace, or we can also segregate the quotas according to priority classes. So I don't know if you're aware of that or not, but pods can have priorities. In this way, we can optimize our clusters by saying some pods are more important than others. And that means if we're short on resources, let the more important pods use the resources while the less important pods can be interrupted. And then we can also scope the quotas according to priority classes. So we can say that the higher priority pods get access to more overall resources than the lower priority pods. And there is an example here. Here's a priority class. This is how you set the priority class for a pod by setting the priority class name to the name of the class that we've defined here. Priority classes allow us to preempt the lower priority pods. That means if the scheduler tries to schedule a pod and there are not enough resources in the cluster for that pod, but that pod belongs to a higher priority class, then it can tell the scheduler, kill the lower priority pods. They can continue later on. You can evict them and maybe place them on nodes that come up later on. And instead of that, run the higher priority pods. And we can also apply resource quotas to priority classes. And we have an example here. So this is how it works. The resource quota isn't applied to the whole namespace. It says this quota only applies to the pods that have a high priority, for example. And there is an example here. We won't be running this now. A few words about limiting resource in practice. So actually we can do, define manually the request and limits per pods. On top of that, we can scope that by limit ranges. And on top of that, we can also scope that by resource quotas. So we can use some, default strategies and policies in our organization. We can say for each namespace, we'll define the limit range object that will define the minimum, the maximum, and the default. Right, and we can even say we're setting a default, different default for stuff like Java and Ruby because they need more memory, and lower limits for Python, PHP, and Node. And the upper bounds set them slightly below your expected node size so that no redundant throttling occurs, or maybe not set CPU limits at all if we're looking at maximum utilization. Then in each namespace, we can create a resource quota object, setting generous CPU and memory limits. And of course, optimization or tuning is a continuous process. So we need to continuously observe the actual utilization, refine, iterate. That's something you can never stop doing if you want to keep your clusters optimized. That's why we are suggesting to automate this process, because actually doing this, manually and actually continuously watching this is a lot of work. And it's also toil. It's not a work that anybody likes to do. The perils of not doing that is, of course, or underutilization or over provisioning in its other name. That means we are requesting resources, we're not using them, we're paying for those resources, money thrown out of the window. And, under provisioning is, of course, taking a toll on reliability. We've allocated resources to our container, allocated too little CPU, it gets throttled, allocated too little memory or too little storage, it gets killed. By the way, once we set a limit range, we can see its definition in the namespace description. So if we now do kubectl describe on our namespace called default, we can see that it has that limit range that we defined initially, right? With the default request and default limit. Let's delete that limit range because we don't need it anymore. So we'll do kubectl delete limit range. Some CPU, some memory. And now describe the namespace, no limit range resources. Okay, so until now we were talking about, you know, the technical knobs that we can turn in order to set the request and limits. But then we're again coming back to the question of how do we define how much our containers actually need? And of course, one practice that needs to be implemented in your organization in order to correctly define this before going to production is benchmarking performance. We looked at a little bit at benchmarking performance already today by running that very basic benchmarking tool called AB, or Apache Benchmark in its full name. Now, that's fine if we do want to run a very small benchmark. That's fine if we're only, you know, hitting one endpoint and we're not setting any payloads, and our benchmark and our performance is not dependent on the kind of payload that our request is sending and the kind of data that our request is retrieving. But in most real-life use cases, it's not that way. Moreover, we do want to be able to test more complex scenarios than just sending something with a lot of threads and a lot of concurrent requests. Usually our production environments are much more dynamic, with some seasonality, with some peaks and some valleys. And that's why we need a more advanced tool in order to do that. We need to be able to simulate load, to check application behavior, to mock different real-life scenarios. There are different types of performance tests we want to run. So we want to measure the average load. We want to measure the performance under spikes, under stress. We also probably want to run some soak tests when we which is a variation of the average load. So for an extended period, run some standard load on a system and see if there is any performance degradation over time, which could be caused by, you know, memory leaking or some instability, etc., etc., etc. So when we test, we need to define, first of all, what's our system under test. We'll use our busy HTTP application again. To remind you, it has an endpoint called CPU that creates CPU load. It has an endpoint called memory that calls memory allocation, and then you can call memfree to release that memory. So we won't do that because we've already done that. We've seen the way it works. And go straight into what was the tool that we're using. So the tool that we've been using very heavily in perfect scale in this last year is K6. I think it's one of the best load and performance testing tools for the cloud native ecosystem, because it's been built in the cloud native ecosystem. It's being built as an open source by Grafana Labs. It allows us to run scripts in very simple to understand and read JavaScript. I don't know if it's an advantage or a disadvantage for you, but yeah, definitely it's pretty easy to write and understand. And relevant to what we're talking about today, it also has a K6 operator that allows us to easily run distributed tests on Kubernetes. And that's what we will be using it for. So the test we're going to run is found in our testing repository in the folder scripts, and it's called API test GS. It defines one scenario that does a ramp up that goes up to 100 virtual users, actually 200 virtual users, if I see correctly what the script here says. This happens in 20 seconds, and then it goes down back to 0 virtual users in another 5 seconds. Let's see the actual script. So it's in scripts API test JS. Scripts. Test JS. Yeah, that's exactly what it does. You can see that it defines the system under test as running on localhost 8080. Or we can define it as an environment variable SUT API URL, and it calls the CPU endpoint, and it just waits for 200 to get returned, and it writes the response body to log. Okay, the test is also defining some thresholds which correspond to our service level objectives that we're defining, right? So we can define the success rate of our requests, and we can also define the threshold as a latency that we expect to have, right? So we're saying here, for example, we're saying that the error rate should be less than 1%, and that the duration shouldn't be lower than 2000 milliseconds or 2 seconds. Okay, so we're expecting the percentile 99 of our requests to succeed under 2 seconds. And we're also saying that if this threshold is crossed, we want this to abort. And that's all there in the script right here. K6 is already installed on your machine, so no need to install that. So let's try to run this. We'll just port forward our service to port 8080 of our host machine. Okay, I didn't deploy anything because I said we don't want to deploy this. But now I realize we do want to deploy this, so we need to deploy. Okay, let's do this. We need these 2 commands first. Okay, let's deploy first. We'll then port forward. Okay, the pod is not running yet. Well, I guess it is running now. Okay, once it's running. And we can now run the test because we have K6 already installed on our client machine. So let's go to another shell here. Exit the watch. Go into position and run. Okay. And this is the test results. So basically what this says is that none of the requests have failed, which is good. And in the end, we're saying that here's a problem. So it says thresholds on the metrics HTTP request duration were crossed. At least one has abort and fail enabled, stopping test prematurely. Okay, so 5 completed, 21 interrupted. And that's why, because we have P95, which is much more than 2 seconds. So we've already arrived at 2.33 seconds. So we've crossed the threshold here. Our application is underperforming. We've bombarded it with requests and it returned our calls in more than 2 seconds, and that's not what we wanted. Now this is nice, but it's not interesting enough because we want to be able to run stuff on Kubernetes. And in order to do that, we'll install the K6 operator. Okay, let's see what this got created. So we go and do kubectl get pod say, and we'll see that there's this new namespace here called K6 operator system, and it deploys something that's called K6 operator controller manager. Now, the way that the tests are running on Kubernetes cluster is that we now have a new custom resource definition called test run. This can define the number of pods that our test will run with. So basically defining a number of clients that the test will run the load on our system under test from. And it also defines where to take the load test script from, with the default option being putting it in a config map. But the config maps are, of course, limited to by the config map maximum size. And when we need something that is more involved, like, for example, something that involves using some data, we want to put that in a persistent volume. And this is the scenario that we're going to be looking at today. Now, what we're going to run here is we'll run a different application. It's a little Golang application called Crypter. What it does, it encrypts some text sent to it with a key that gets regenerated every 30 seconds. And if within these 30 seconds, this key gets sent back to the application, it will decrypt the text. Now, I wanted to use something that deals with encryption because this usually creates more than standard load on CPU and memory. This application is still quite performant, so it also creates some unnecessary load on CPU and memory to make things more interesting. You're welcome to go to the repo and look at the code later. Definitely don't learn from it because this is not production level code. So let's do this. We'll clone the application. We'll go into the application directory. So, sorry, clone the repo, go to the repo directory and apply the deployment YAML. Okay. Okay, we have that CryptoPod running. Let me clean this up. I want to delete the BZHTTP deployment because I don't need it anymore, and I want to delete the pod called BZHTTP. And I want to delete the pod that I used to show the ephemeral volume problem. Okay. So we have one pod here with one service that exposes it. It's called Crypter. There's also this service that I don't want. Okay. Now that we have this, we can run the test. So the test has been provided to us in the repo. So if we go into that, we'll have a YAML that creates a persistent volume and populates it with some data that we'll then use in the test. Okay, so let's run this first. Okay, we don't need this anymore. Okay, let's look what we just did. So I'll look at the test volume. So what this does is it creates a persistent volume claim called perf test. Okay, and it then creates a pod that mounts that persistent volume claim as a volume. And inside that, it runs this container based on this image that has the test script built into it. So it mounts the volume and it copies all of the tests that are found inside that container into the persistent volume. And the result of that is at a certain point, our test volume pod gets completed and we get a persistent volume claim called perf test that has the script in it. Now, once we have that volume, we can now run our test. Let's look at the test. It's there in the file called test run. So when we look at that, okay, so what this defines is this defines a test run that runs with a parallelism of 2. It says that the script comes from the volume claim called perf test. Here it is. Okay, and inside that volume, there is a file called API test.js. Okay, and it also provides some environment variables for the runner, which is the API URL for that crypto service that we want to test. Okay, and let's see what happens when we create that. So we'll apply it. Let's now watch what happens. We'll do kubectl get pod. We'll see that this creates 2 new pods called crypto load, and there is also another pod called crypto load initializer. At a certain point, the initializer gets completed while the crypto load 1 and 2 start running. We can look at their logs by doing kubectl logs crypto load 1. Okay, and we're seeing they're doing some job there, encrypting and decrypting stuff. while that's running, we can do kubectl top on pods to see that our cryptor pod went up to pretty high CPU utilization and memory utilization. And once the cryptor load pod's complete, let's see, kubectl get pod. Okay, we see that at a certain point they exit with an error. And once that happens, we can do top again and see that, well, our CryptoPod is not releasing CPU and memory yet. It will take it some time to cool down. But we can look at the logs from the load test pods by running this on my cryptor load one, whatever it's called. Okay, and we'll see the result of the test, just as we saw it in the console before. Okay, and we'll see that quite again, the metric on HTTP rec duration has been crossed. And this time, we're reaching about 18 seconds on a call, and that's definitely not acceptable. And of course, a test that you can do when you have the time, and I see we don't have the time, we only have about 10 minutes left for this training. You can, of course, always try to change the settings on the deployment. You can limit the deployment to 200 millicores of CPU and, for example, 50 megabytes of memory, and then create a new test and see how that affects performance. Now, oh yeah, another thing I think that we didn't notice is that, okay, yeah, right, okay, this crypto deployment, it gets slow, so the test fails, but the pod itself continues working, right? If we limit the pod, the crypto pod, to 50 megabytes of memory, or even to 100 megabytes of memory, at a certain point, it will get out of memory killed, right? Because if we look at it, okay, right now it's cooled down to 20 megabits of memory again, but at its top, it used to take something like 160, 170 megabytes of memory. So under load, it will get out of memory killed. Raising the memory limit will prevent it from failing, but it will still get throttled if it has a CPU limit. Now, if one instance of Cryptor with the limits that we enforced cannot handle the load, maybe we should try scaling it out. But what will be our scaling criteria? How do we adapt our requests and limits to support our SLOs? Because, you know, we have some suggestions and some assumptions regarding our load, but the production load may differ. So in order to actually continue adapting our resource requests and limits according to the actual load, we need something automatic in our cluster that will give us recommendations and finally set the request and the limits. Now, I see we don't have enough time, so we'll just touch upon this. And I invite you to use the examples in the slides that are available to you after the training in order to see this in action. So basically, you can always use vertical pod autoscaler. You have the commands here to deploy it to your cluster. You can rerun the test on busy HTTP, or you can define VPA on Cryptor, and you'll see that its automated updater will automatically update the requests and limits for your containers, and it will recreate the pods and recreate the containers, and they will be created with the actual requests and limits fitting the utilization that the VPA observes. The good part about VPA is it's easy to set up, it's free and open source, it only requires metric server to operate, and of course, no guesswork when setting resources. The bad part about the VPA is, first of all, you have to configure it per workload. So for each workload, you need to create a custom resource called VPA. It relies on the decay and histogram algorithm, and that means it's not aware of the changes that we apply to our applications when we deploy new revisions. It blocks config changes. So if we want to manually change the request and limits definitions for our workloads, we need to turn it off because otherwise its admission controller will interfere. And it's not a very good fit for highly volatile workloads because it becomes very disruptive. And also it's totally unaware of your cluster node limitations. So in theory, if it says it sees some pod utilizing a lot of memory or a lot of CPU, it will pull up its request to whatever that pod is requesting, and then probably, or maybe you don't even have nodes that can satisfy these requirements. And because VPA is node agnostic, it's not a very good fit once you start implementing cluster autoscaling. That's VPA. Of course, another way of scaling would be horizontal scaling, and that's what the horizontal pod autoscaler does. The horizontal pod autoscaler allows us to change the number of pods in a workload according to resource utilization. It can work on CPU, it can work on memory, it can also work on custom metrics that we're defining, even though that's harder to set up. Here in the slides, we have some examples on how to run in CHP in action for CPU and memory. We'll definitely go through this if you're interested. Now, HP also has its downsides. One of the downsides, if we set its threshold to the default 80% of utilization, that means that in most cases, we're just wasting 20% of resources for that either CPU or memory that we're setting it with. So we usually want to pinpoint the resource utilization very finely, very correctly. The VPA, for example, doesn't know how to work with HPA in a good way. Perfect scale in that aspect works better. And because we now need to wrap this up, the final thing I'd like us to do is go to the perfect scale interface with that cluster that I connected to it, and maybe you also signed up and connected your own cluster, and look at that cluster and look at all the stuff that we've been running here. So one thing we can see is, for example, that perfect scale right out of the door, it finds different resource allocation risks that we have in the cluster. So for example, for this workload here, it says your CPU request is under provisioned. You're using more CPU than you're actually allocating, and you're not setting any memory request. And it provides a recommendation that says you should set your memory to at least 35 because that's what you're using. And it also says you need to set your CPU much higher because right now you're requesting 50 millicores, and that's definitely not enough because we've seen our workload occupying the whole CPU, right? And for that cryptor deployment that we did here, again, it says you're not setting this correctly because you're utilizing more memory than you actually giving your deployment. Well, actually this says not set, not set. Oh, right, because we haven't said this yet. So sorry, yeah, it's the restarts observed here are 0. Okay, why did I didn't see this correctly? Okay, basically it says you haven't set anything based on the workload that I saw here. You need to set the requests and limits for memory and CPU. And if we apply these recommendations, it will work much better, saving us money and also making our workloads more reliable. Okay, we don't have time to go deeper into this, but I hope this gave you some indication on how PerfectScale can help you. Now, the great thing about this is, of course, not just looking at recommendations. The great thing about this is that once you're happy with the recommendations, you can set this to be automated. We have a CRD that allows you to basically say, optimize all of the workloads in my cluster, and they will keep them optimized. So it will continue setting the requests and limits according to what your workloads are actually using, being as non-disruptive as possible, and continuously optimizing the cluster both for cost and performance and reliability. If you signed up today, you can reach out to me later and we'll enable automation for you. It's not included by default in the community edition, but definitely reach out to me and we'll enable the automation for you. And if not, then definitely consider signing up and connecting your production cluster or pre-production clusters to this and see if this helps you in any way. Okay, folks, I think we're done for today.